Have you ever wondered how massive construction equipment manages to lift tons of weight, or how factory robots move with such precision? The answer often lies in two powerful technologies: pneumatic and hydraulic systems. These systems, though unseen by most, are the driving force behind countless applications, from the brakes in your car to the robotic arms assembling complex electronics. Pneumatic systems harness the power of compressed air to generate force and motion. Imagine filling a balloon with air. The more air you pump in, the more pressure builds up, and this pressure can be used to do work. Hydraulic systems, on the other hand, utilize incompressible fluids, typically oil, to transmit power. Picture a syringe filled with liquid. When you push the plunger, the fluid transmits that force to the other end. These systems, though relying on different mediums, share a common goal: to convert energy into controlled linear or rotary motion. They provide the muscle behind countless operations, making them indispensable in our modern world. Let's delve deeper into the intricacies of each system to understand their unique characteristics and applications. Pneumatic systems are all around us, often working silently and efficiently behind the scenes. They are responsible for a wide range of applications, from the simple act of inflating tires to powering complex industrial machinery. But how do these systems actually work? At its core, a pneumatic system utilizes compressed air as its power source. Air, readily available in the atmosphere, is drawn in by a compressor and compressed to a high pressure. This compressed air, now containing stored energy, is then channeled through pipes and hoses to various components. Imagine a bicycle pump. As you push down on the handle, you are compressing air within the pump. This compressed air is then forced into the tire, inflating it. This simple analogy illustrates the basic principle of pneumatics, using compressed air to generate force and motion. Pneumatic systems rely on the relationship between pressure, volume, and temperature. When air is compressed, its volume decreases and its pressure increases. This pressurized air acts as a reservoir of potential energy, ready to be released and converted into kinetic energy to perform work. To effectively harness the power of compressed air, pneumatic systems rely on a network of essential components working in harmony. These components work together to generate, control, and deliver pressurized air to where it's needed. At the heart of any pneumatic system lies the compressor. This vital component is responsible for drawing in atmospheric air and compressing it to the required pressure level. Think of it as the heart of the system, pumping pressurized air through the pneumatic circulatory system. Once compressed, the air needs to be regulated and controlled. This is where valves come into play. Valves act as gatekeepers, directing the flow of air to specific parts of the system. They can be programmed to open and close at precise times, ensuring that actuators receive the correct amount of pressure. Actuators are the muscles of the pneumatic system, converting the pressurized air's energy into mechanical motion. These can be cylinders, which use air pressure to extend or retract a piston rod, or motors, which convert air pressure into rotary motion. While pneumatic systems rely on the compressibility of air, hydraulic systems leverage a different principle: the incompressibility of fluids. This means that hydraulic fluids, unlike air, resist compression, making them ideal for applications requiring high force and precise control. Imagine a syringe filled with water. No matter how hard you press the plunger, the water itself won't compress. Instead, it transmits the force applied to it directly to the other end of the syringe. This is the fundamental principle behind hydraulics. Hydraulic systems utilize a pump to pressurize a hydraulic fluid, typically oil. This pressurized fluid is then transmitted through hoses and pipes to various components, similar to how blood flows through our circulatory system. When this pressurized fluid reaches an actuator, it exerts force, causing it to move. The incompressible nature of hydraulic fluids allows for the transmission of power with minimal loss. This makes hydraulic systems highly efficient in converting mechanical energy into controlled linear or rotary motion. Section 5. Key components of hydraulic systems. Harnessing fluid power. Hydraulic systems, like their pneumatic counterparts, rely on a network of interconnected components to function effectively. These components work in unison to generate, control, and transmit hydraulic power. The pump acts as the heart of the hydraulic system, drawing hydraulic fluid from a reservoir and delivering it to the rest of the system under pressure. Pumps come in various designs, each suited for specific applications and pressure requirements. Valves in hydraulic systems serve a similar purpose to their counterparts in pneumatic systems. They regulate the flow and pressure of the hydraulic fluid, directing it to specific actuators or components as needed. Valves can be manually operated, mechanically actuated, or electronically controlled. Actuators in hydraulic systems, often cylinders or motors, convert the hydraulic fluid's energy into mechanical work. Cylinders, for example, use hydraulic pressure to extend or retract a piston rod, while hydraulic motors convert fluid power into rotary motion. Section 6, Pneumatic versus Hydraulic, a head-to-head comparison. Both pneumatic and hydraulic systems offer unique advantages and disadvantages, making them suitable for different applications. Understanding their strengths and weaknesses is crucial in selecting the right system for a particular task. Pneumatic systems are generally preferred for applications requiring lower forces and simpler designs. Air is readily available, making these systems relatively inexpensive to operate. Additionally, the use of air eliminates the risk of leaks contaminating the environment, making them suitable for cleanroom environments. Hydraulic systems, on the other hand, excel in applications demanding high force and precise control. The incompressible nature of hydraulic fluids allows for greater force transmission, making them ideal for heavy-duty applications. However, hydraulic systems can be more expensive to implement and maintain due to the cost of hydraulic fluids and the need for specialized components. The choice between pneumatic and hydraulic systems often depends on factors such as the required force, speed, precision, cost, and environmental considerations. Understanding these trade-offs is essential in selecting the most appropriate system for a given application. Section 7, Applications in Everyday Life. From dentist drills to theme park rides. Though often hidden from view, pneumatic and hydraulic systems play a vital role in our everyday lives. From the tools we use to the vehicles we drive, these systems are constantly at work, making our lives easier and more enjoyable. Pneumatic systems are commonly found in applications requiring lower forces and simple movements. For example, dentists use pneumatic drills, powered by compressed air, for precision work on teeth. The brakes in heavy vehicles like buses and trucks often utilize pneumatic systems for their reliability and stopping power. Hydraulic systems, with their ability to generate high forces, are well suited for applications requiring heavy lifting or precise control. The amusement park rides that thrill us with their speed and agility often rely on hydraulic systems for their operation. Similarly, elevators utilize hydraulic systems for their smooth and controlled movement. From the chairs we sit on to the tools we use, pneumatic and hydraulic systems are seamlessly integrated into our daily routines, often working silently and efficiently behind the scenes. Section 8. Industrial Applications. Powering automation and heavy machinery. In the industrial landscape, pneumatic and hydraulic systems are indispensable, forming the backbone of countless manufacturing processes and heavy machinery operations. Their ability to generate controlled, linear and rotary motion makes them essential for a wide range of tasks. Pneumatic systems are commonly employed in factories for tasks such as operating robotic arms, controlling conveyor belts and packaging products. Their speed, reliability, and relatively low cost make them ideal for these repetitive tasks. Hydraulic systems, with their high-force capabilities, are the powerhouse behind heavy machinery used in construction, mining, and agriculture. Excavators, bulldozers, and cranes all rely on hydraulic systems to move massive amounts of earth and materials. The versatility of these systems extends beyond traditional manufacturing and heavy industries. They are also finding applications in renewable energy, aerospace, and medical devices, demonstrating their adaptability and continued relevance in a rapidly evolving technological landscape. Section 9. Conclusion: choosing the right system for the job. Pneumatic and hydraulic systems, though often unseen, are the unsung heroes of our modern world. They provide the muscle behind countless applications, from the tools we use to the machines that power our industries. Each system, with its unique characteristics, offers a distinct set of advantages and disadvantages. Pneumatic systems, utilizing the compressibility of air, are well suited for applications requiring lower forces, speed, and simplicity. They are relatively inexpensive to implement and maintain, making them attractive for a wide range of tasks. hydraulic systems, leveraging the incompressibility of fluids, excel in applications demanding high forces, precise control, and the ability to hold a load in place. While generally more expensive than their pneumatic counterparts, they offer unparalleled power and control for heavy-duty applications. Understanding the strengths and limitations of each system is crucial in selecting the right technology for a particular application. By carefully considering factors such as required force, speed, precision, cost, and environmental impact, engineers and designers can harness the power of these systems to create innovative solutions for a wide range of challenges.